After studying this module, you shall be able to know about spin crossover, also referred as spin transition or spin equilibrium behavior. Learn spin crossover is a phenomena that occurs in some metal complexes wherein the spin state of the complex changes due to the external stimuli such as a variation of temperature, pressure, light irradiation or an influence of a magnetic field. Identify various spin transition curves, evaluate the extent of splitting in octahedral complexes.
Spin crossover. Spin crossover, sometimes referred to as spin transition or spin equilibrium behavior, is a phenomena that occurs in some metal complexes wherein spin state of the complex changes due to external stimuli such as a variation of temperature, pressure, light irradiation, or an influence of a magnetic field. Spin crossover refers to the transitions between high to low or low to high spin states. This phenomena is commonly observed with some first row transition metal complexes with a D4 to D7 electron configuration in octahedral ligand geometry. As we already know that metal ions with any of the D7, D5, D6 and D7 configuration exhibit two possible electron configurations in the octahedral ligand field. These high spin and low spin states of an octahedral complex will have the same energy when delta is equals to P. If in a coordination complex, the crystal field splitting is close to the delta is equals to P value, then the energy difference between the two spin states of the complex will be in the range of the thermal energy kT. Further, in octahedral field, if the energy of the two spin states is same or nearly same, the low spin and high spin states can coexist in equilibrium. This phenomena is referred to as spin state equilibrium. The magnetic moment for these complexes will be anomalous. An example of a metal ion that can exist in either a low spin or high spin state is Fe3 plus in an octahedral ligand field. Depending on the ligands that are coordinated to this complex, the Fe3 plus can attain a low spin or a high spin state. As we can see on the screen, consider the low spin complex hexacyano iron 2 plus and the high spin complex hexafluoro Fe2 plus. The Tanube-Sugano diagram of these two complexes is shown here. Now, change in the temperature will lead to an alteration in the population of the two spin states. The Tanube-Sugano diagram of the two complexes reveals that if the ground state of the complex is low spin, then an increase in temperature will increase in the population of high spin state. It explains the magnetic susceptibility will increase. Second, a decrease in temperature will increase in the population of low spin state. It explains the magnetic susceptibility will decrease. On the other hand, if the ground state is high spin, then the reverse of first and 2 will hold true. The Tanube-Sugano diagram of these D6 complexes also show that near the crossover point between weak and strong field, the difference in energy between the spin-free and spin-paired ground states becomes very small. Within this region, it is reasonable to expect that both spin states may coexist in equilibrium and that the degree to which each is represented will depend on temperature. The most interesting example of spin crossover is the complex shown on the screen. At high temperature, this complex exists as high spin with four unpaired electrons and a moment consistent with four unpaired electrons is observed. But as the temperature is lowered, a sharp drop in magnetic moment is observed at 175 Kelvin and low spin form of the complex becomes dominant. This indicates that at 175 Kelvin, the complex exists as both high spin and low spin complex. Thus, the magnetism of the complex changes sharply at 174 Kelvin as shown here on the screen. In solution, these systems are fairly straightforward. The change in magnetic susceptibility with temperature can be interpreted in terms of heat of conversion of one isomer to another. However, treatment of the system as an equilibrium between two spins gives delta H is equals to 3.85 kilocalories per mole and delta S is equals to 11.4 for the high spin to low spin conversion. On the other hand, spin crossover in solids is a complex phenomena because of cooperative structural changes and changes in the energy separation of high spin and low spin states with temperature. The spin state equilibrium is not possible in an octahedral complex of a metal ion with 3d8 configuration. However, the spin state equilibrium has been reported in several 3d8 nickel 2 plus complexes. In such a complexes, there is distortion of regular geometry or coexistence of two distinct stereochemistries, thereby leading to two spin states that are S is equals to 1 and S is equals to 0. The tetrahedral complexes can only exist in high spin state since delta tetrahedral is much lower than P. So there will not be any spin state crossover region and hence no spin state equilibrium. Thermal spin transition occurs nearly exclusively with coordination complexes of 3D metal ions. This is not expected for 4D and 5D transition metal compounds because strength of the ligand field increases notably relative to the analogous 3D compounds and is generally much greater than the spin pairing energy. Hence, virtually all 4D and 5D transition metal complexes show low spin behavior. Spin transition curves. Spin crossover phenomena can be represented by spin transition curves. In spin transition curves, high spin molar fraction is plotted versus T, temperature. You can see on the screen a gradual spin transition curve on the left, an abrupt transition with hysteresis middle and a two-step transition at the right. For a transition to be considered gradual, it typically takes place over a large temperature range, even up to several hundred Kelvin, whereas For a transition to be considered abrupt, it should take place within 10 Kelvin or less. High spin molar fraction can be calculated by dividing molar concentration of high spin complex by the total concentration of the complex. These curves indicate that a spin transition has occurred in a metal complex as temperature changed. The gradual transition curve is an indication that not all metal center within a complex are undergoing the transition at the same temperature. The abrupt spin change with indicates a strong communication between neighboring metal complexes. In the latter case, the material is bistable and can exist in the two different spin states with a different range of external stimuli for the two phenomena, namely low spin to high spin and high spin to low spin. The two-step transition is relatively rare but is observed, for example, with dinuclear spin crossover complexes for which the spin transition in one metal center renders the transition in the second metal center less favorable. Factors affecting spin crossover behavior. The crossover region is very sensitive to several factors. In the discussion that follows, we shall bring out the condition under which crossover occurs, chemical factors, effect of metal ligand bond distance. The transition from high spin to a low spin state is carried out by the transfer of one or two electrons from the higher energy Eg set to lower energy T2g set. As we know that the Eg set orbitals point directly at the ligands approaching right along the coordinate axis, while the T2g set orbitals are between the point charges. This enhances the repulsion between electrons of the metal Eg set orbitals, the donated electron pair from the ligand, raising the energy of these metal orbitals relative to the other three. Thus, an Eg2 T2g transition is most likely to reduce the metal ligand bond distance R. Since delta is also dependent on R, it follows that such a transition increases delta by 10 to 20%. The potential energy curves for the high spin and low spin complexes are shown here. The low spin state has its minimum energy at smaller r value than high spin state. In the figure, A and C depict high spin and low spin ground states. However, B shows the equilibrium situation where energy of two spin states are quite close, resulting in crossover. Effect of intra-ligand substitution. A substitution in the ligand backbone often changes delta and B substantially due to first the sigma and pi interactions, second the steric effects. This leads to a modification in magnetic property. This has been illustrated with the group of the complexes shown on the screen. Exchange of H for CH3 in either the 2 or 9 position of the 3-phenanthroline ligands weakens the ligand field strength due to steric hindrance, whereby the metal donor atom distance is elongated, and the low spin behavior of the complex turns to spin crossover behavior of the tris 2CH3 phenanthroline complex. If both the 2 and 9 positions of these 3 phenanthroline ligands are substituted by CH3, the steric hindrance is even stronger and weakens the ligand field strength further, yielding high spin behavior of the tris 2,9 CH3 twice complex down to very low temperatures. It was found that a combination of steric hindrance due to bulkiness and an electronic influence of the substituent on basicity of the coordinating N atom are responsible for the influence on the spin crossover behavior. The paramagnetic property of the complex increases in the order Y is equals to H, CH3O, CH3 and Cl. One has also found that a change of the substituents at positions not adjacent to the coordinating N atom in the phenanthroline ligand does not influence the spin state in comparison to unsubstituted complex. Effect of counter anions. A more subtle chemical influence is the variation of the anion associated with a cationic spin crossover system. In ionic lattices with cationic spin crossover complex molecules and uncoordinated counter anions in lattice positions remote from the metal center, the ion can nevertheless exercise a strong influence on the spin crossover behavior through cooperative interactions. These interactions can result in the displacement of the transition temperature even to the extent that spin crossover is no longer observed or may also cause a fundamental change in the nature of the transition. For example, from abrupt to gradual. For the 2-picolyl amine complex of iron, salts, the degree of completion and steepness of the spin transition curves increases in the order iodide to bromide to chloride. Effect of non-coordinated solvent molecules. The nature and degree of solvation of salts or neutral species can also alter the transition temperature. The nature of solvate molecules in the complex determines the transition temperature. Various solvates of the spin crossover complexes with solvent, ethanol, methanol, water were studied to explore the influence of the non-coordinated solvent molecules on the spin crossover behavior. The spin transition curve of the complex with solvent ethanol shows a rather steep transition near 115 Kelvin, with methanol shows a gradual spin transition near 150 Kelvin. The monohydrate and dihydrate exhibits a very broad hysteresis loop with transition temperature near 200 Kelvin and near 290 Kelvin respectively, and the dehydrated sample exhibits no spin transition at all but remains in low spin state. Effect of hydrogen bonding. Hydrogen bonding can also impart a major influence on both the transition temperature and the nature of the transition, providing the structural link for the communication between the crossover centers. Thus, the extent to which an ion or solvate molecules can form hydrogen bond with the spin crossover center will likely influence the nature of transition. Hydrogen bonding also seems to play a significant role in changes in spin crossover behavior accompanying hydration, dehydration processes. It has been proposed that hydration will generally result in a stabilization of low spin state through hydrogen bonding of the water with the ligand. This does not indeed seem to be the case for most hydrates, but in a cationic spin crossover system where the ligand is hydrogen bonded to the associated anion only and this in turn is bonded to the water, the effect can be reversed. It explains loss of water can also result in stabilization of the low spin state. Effect of metal dilution. The effect of dilution of spin transition complexes into the lattice of isostructural species which do not or cannot show spin crossover has proved to be very diagnostic of the function of cooperative interactions in influencing the nature of spin crossover in the solids. This was shown first for the mixed crystal series of iron 2 plus X, Zn 1 minus X 2 picolylamine 3 chloride dot ethanol with X ranging from 0.007 to 1. Zinc was chosen in this metal dilution study because it has the same crystal structure as the analogous iron 2 complex. The transition curve is abrupt for the neat compound where X is equals to 1 but becomes increasingly more gradual with increasing dilution as is generally found for thermal St in liquid solutions. Moreover, the transition is shifted to lower temperatures, reflecting increasing stabilization of the high spin state. These results clearly support the existence of cooperative elastic interaction between the spin crossover metal centers as the transition proceeds. The nature of such cooperative interactions is purely mechanical. Physical factors. Effect of applied magnetic field. As we know that the spin transition phenomena involves different spin states having different magnetic properties, so the spin crossover behavior is expected to respond to an applied magnetic field. This indicates a change of the spin transition curve with applied magnetic field. Perturbation of a spin transition by an external magnetic field is predicted by thermodynamics and the magnitude of the change in transition temperature can be calculated if the magnetic response of the molecules involved is known. An experiment with the sample of a complex shows that the transition temperature measured by susceptibility measurements in an applied field of 1 Tesla shifted by minus 0.112 to 0.04 Kelvin when the field is increased to 5.5 Tesla. Effect of sample preparation. Mechanical treatment of the samples or different synthetic procedures have been shown to strongly influence the spin crossover behavior. For instance, ball milling or crushing crystals in a mortar often resulted in the flattening of the spin transition curve with an increase of the residual high spin fraction in the low temperature region. The spin crossover characteristics may also be influenced by the synthetic procedure as illustrated for the complex shown on the screen. This can be prepared in two principal ways: by precipitation from methanol or by extraction with acetone of a phenanthroline molecule from the complex shown on the screen. The samples prepared by both methods have the same chemical formula but exhibit different spin crossover behavior. The compound obtained by the first method shows a smooth spin transition with a significant high spin fraction at low temperature, whereas that prepared by the second undergoes a sharp and complete spin transition. The origin of these effects is mainly crystal defects introduced during sample preparation, either by milling or rapid precipitation. The particle size has also been reported to play an important role. Effect of pressure. Increase in external pressure shortens the metal donor atom distances of spin crossover complex and increases the ligand field strength at the metal center. It is therefore expected that an increase in the pressure stabilizes the low spin state and increases the transition temperature. An increase in pressure on the complex is likely to shift the high spin to low spin equilibrium in favor of low molecular volume. It explains towards the low spin form. For example, 4 coordinated complex of nickel 2 plus with ligand NN diethyl amino propion imine shows an equilibrium between the tetrahedral and square planar species in solution. The tetrahedral form of this complex is paramagnetic and the square planar form is diamagnetic. With an increase in the pressure, the proportion of high spin square planar form increases. However, proportion of high spin tetrahedral form decreases. This results in the decrease of magnetic susceptibility of the sample. From the magnetic moment of high and low spin forms, the equilibrium constant at a given pressure can be calculated as shown on the screen. It is noteworthy to mention that nickel chloride exists in only one spin state, shows no change in its magnetic susceptibility in the pressure range from 1.013 into 10 raised to power 5 to 3.039 into 10 raised to power 5 kilopascal in water or chloroform.
In this module, we discussed spin crossover or spin equilibrium behavior, which is a phenomena that occurs in some metal complexes wherein the spin state of complex changes due to external motivation or an influence of a magnetic field. Spin crossover refers to the transition between high to low or low to high spin states. The various spin transition curves. In spin transition curves, high spin molar fraction is plotted versus T. The spin crossover region is very sensitive to several factors. These factors can be chemical factors as well as physical factors. The chemical factors include effect of metal ligand bond distance, effect of intra-ligand substitution, effect of counter anions, effect of non-coordinated solvent molecules, effect of hydrogen bonding, effect of metal dilution. Physical factors include effect of applied magnetic field, effect of sample preparation and effect of pressure.